Okay, we're going to see if I can make this presentation work here. So what we're going to do is this is the transformer. Uh, this is the transformer lab, and this is a video lab going on to YouTube. So I'm going to see if I can make this work. We'll find out. Anyway, we have two types of systems on this campus. We have a 20 kV, 25 kV system, which is really 23.9. It's a 23.9 kV system, and that is a VAB value, line voltage value. It's mostly delta, because we don't run a neutral like we could run for Y, but you can have a grounded Y system, which is a 3-wire or 4-wire system also. Anyway, these are our 25 kV elbows. This is a heat shrink right here. You put it on with a heat gun. You've got to prep the wire, so many inches for this, so many millimeters for this, blah, blah, blah. You have a ceramic guide pin, and then I'm going to show you in a minute another pin that's out of the elbow, and it fits into a lug on the end of the wire. This is a ceramic or capacitive test point right here. Basically, you can do a lot of things with that. You can check and see exactly what the voltage is. If you have the right meter, it'll tell you exactly what the voltage is. You can also go in there and compare, say, the A phases of two different lines and see if they are both the A phase. If the voltage between your digital multimeter, if you put your lead on that end in there, that capacitive test point, and the voltage difference between the two is 0, then you're on the same phase. And if it's like 48, maybe 60 volts, then you're on the wrong phase. Anyway, here's with the cap off, here's the capacitive test point. Like I say, you can do some things with it, check and see exactly what the voltage is, or check phasing on it. This is a ground wire. It just grounds the elbow. Not a big thing, but you do need your ground wires. Here is the ceramic guide pin. This is the ceramic part of the guide pin, and this is the actual conductor of the guide pin. So you can, that guide pin, what you can do with it is this just helps it go into the mount, and then this actually hits the conductor. It's screwed in right here. This is just a screw that screws into a lug on the end of the conductor, and it just, this thing just plugs into there's a little hole right there that ceramic goes into, and it just stabs onto that guide, and there's a rubber grommet around here that makes it waterproof. And then you've got this hooks to the, well, I guess this could be a switch module if you want. Maybe on the next one I'll give you an example of a switch module. Anyway, so that's an elbow. Here's the wire that this elbow is on. You've got a concentric neutral that just coils up, wraps up into a ground, and goes on to wherever the ground is in that system. You have a semicon right here. This is the semicon, this black stuff right here is a semiconductor. Basically, it controls eddy currents. So eddy currents are currents that come out 90 degrees to perpendicular to the magnetic field. And so this semiconductor basically controls the magnetic field and the eddy currents and keeps them inside the insulation and doesn't let them get outside where they could cause damage. Uh, you have this orange is the insulator, that orange piece right here. That is the insulator. And then you have an aluminum, stranded aluminum conductor in there. So that's an elbow and what it's terminated on, that type of stuff. Also, in a transformer, you have two different types of fuses. This is an internal fuse link. Basically what it is you just take this thing apart, stick a fuse link in there, put the ends back on there, stick it back into the tub and its little mounts and tub of oil, and so if it blows a fuse, you can easily just go in there, turn it off, pull that link out, pull it open, put a new link in, close it back up, and stick it back in the oil, and it's insulated and it works. So it's like a fuse. If your grandmother has those little screw-in fuses, this is basically the same thing, except, usually it's about 2.5 times, depending on who you talk to, about 2.5 to 7 times what the transformer is rated for power-wise, kVA. The second type of voltage that we have on campus is 5 kV, which is really 4160 volts, and that also is a VAB value. Remember, everybody talks about line voltages. They don't talk about phase voltages. They talk about VAB, line voltages. That's the assumption. That's always the assumption. Notice that here, this bolts up to the spade lug. There's always going to be a lug on the transformer or the switch, and this end is going to bolt up to it. It's kind of like it's a terminator. It's like an elbow, but this is more like an original stress cone, which nobody makes anymore. These things are either shrink wrapped. You pull out this plastic spring and it collapses onto the, kind of like heat shrink, collapses onto and insulates everything, but it's called cold shrink. And then you also have heat shrink ones. So I don't know what this one is. It's probably a cold shrink. Problem with heat shrink is if you burn that insulation, you got to strip it off and completely put a new one on there. This is a different type of cable. Like I say, it's a 5 kV cable. The insulation's thinner, less insulation in there, but it's still got, the outer insulation. This has a ground on it right here, a ground tab that takes that, makes sure that all those eddy currents and everything goes to ground off the semiconductor. This is called a ribbon or tape shield, completely different from the concentric neutral. You have the semiconductor. That's this black stuff right here around the wire again. Let me get a little bit better picture of this. Yeah, here we go. So you got the insulation right here. That's that yellowish stuff. You got the semiconductor, which is black. And like I say, it keeps the eddy currents contained. You've got, in this case, this is a copper conductor. It's not an aluminum conductor like the other one. And then you've got the tape shield. And it's just like a band of tape around there, and it keeps everything together. So that's the type of connectors you can have on a 5 kV system or a 25 kV system. You can have elbows on the 5 kV system. You can have terminators on the 25 kV system. So, this is just to show you how we terminate this stuff here on campus. So the next thing we have is, this is a transformer lab. So you have the front view and the side view of the transformer. The front view, the high side is always on the left side, always on the left side. And the low side cabinet is always on the right side. And on this cabinet right here, you have a lock. And that lock, you take the lock off, it's got a 5-sided bolt that you unscrew, like mayonnaise jar. If you hold a mayonnaise jar, you want to unscrew it. How do you do it? Righty-tighty, lefty-loosey. Some people call it mayonnaise jar. You open that thing up. On the back side, then what you have is you have the radiator right here in red. You have the oil tank, which is in the blue right there. And then you have the wire cabinet, which is what you're looking at in the front view. So the different parts, if you remember on the video that you saw, the terminators were coming out of the top of that one on the video. You have to open the doors on this one to get to the terminals of the transformer. So different types of transformers, but if it's a cabinet type, which is, or a pad mount, which is what this is, pad mount with an internal terminator cabinet, then the high voltage side is always going to be on the left, and the low voltage side is always going to be on the right. So here we go, some more. All right, here's the open doors. Well, let me go back a little bit one more time. So one of the things, if you ever go out in the field, if you're ever a facilities engineer or something like that, safety always comes first with this stuff. You don't want to get hurt. You don't want to have to call somebody up and say, hey, your husband's not coming home or your son's not coming home tonight. You always keep this area clear. You never put anything on there. You also never put anything on top of the piece of equipment. If you happen to knock it off and you go to catch it and you stick your hand in there, you're dead. End of story. You're going to die. It's unforgiving. It does not forgive. You want to keep this area clean just in case something happens, and you want to keep a nice pathway out of there. Just in case something happens, you want to be able to get out of there. And you don't want to trip over somebody's tools or something like that, fall on your face, and something happens there. So you always keep safety in mind. Make sure they don't put anything on top of a switch or a transformer or any other kind of gear, and you always keep a nice safe pathway out and away from it just in case something does happen. So here we are. We have the high side and the low side. Both cabinets are open. Once again, left side is the high side and the right side is the low side. You can see the basic layout of the transformer. We're going to take the high side first, and I'll show you what's going on in there. So here's the high side of the cabinet. Notice the phasing. The black tape is the A phase or the 0 degree phase. The red phase is the B phase, and the blue phase is the C phase, which is plus the 120 degrees from the A phase. Part of the problem is, really and truly, you don't know which one is the A phase, the B phase, and the C phase. All you know that one's going to be close to 0, one phase is going to be close to minus 120, and one phase is going to be close to plus 120. You go to Gulf Power, and they call them ABC. You go to Alabama Power, and they call it 1, 2, 3. They do a 1, 2, 3 phase, not an ABC phase. You go over to Florida Power and Light, and they do 0, 1, 2. Just depends on how they start this stuff off and what they stay with and stick with, and So if you look right here, here's your elbows. They stab on, create a nice waterproof connection, and it just lifts up and pushes in, and then you push it in real hard. You have a hot stick, what's called a hot stick. It's got a little hook on the end of it, fits in that eyelet of the elbow, and you pull it off that way. On this one, you also have lightning arresters. Lightning arresters, if the transformer gets hit by lightning, what you want the lightning arresters to do is instead of damaging the interior of your transformer, you want to give it a nice quick ground path, and that's what these do. You see those ground wires down here, those copper ground wires, and they hook up down here to the ground. If you could look in here, there's a ground ring that goes all the way around that transformer, and there's also a ground ring in the vault, which I'll show you here in a minute, inside the vault down there, and all the stuff's connected to two 10-foot 3/4 inch copper ground rods that go into the ground. So keep on going up. Again, here's the lightning arrestor, all it does is just a quick path for lightning to go to ground. The most important thing in here is your tap changer. The tap changer is basically so you can regulate the voltage, the output voltage of your transformer. If anybody works for ICT or works over at the Undergraduate Learning Center, I know a couple people over there are always complaining about low voltage in the summer. We could go over there and tap it one so that we could up the voltage, and it depends on the excuse me, it depends on the nameplate and what the tap ratings are and all that stuff. But you just turn the transformer off, pull this tap change switch out, turn it to the next one, and you'll get, depending on which way you want to go, high voltage or low voltage, depending on what's coming in and what you want coming out. And here is the formula that they gave you on the that transformer video. You had a high side, the nominal voltage, or what the actual voltage is. Some people call it nominal. It can also be the actual value of the voltage. And then the rated voltage is the rated voltage of the transformer. Called transformer nameplate. And we'll get to the nameplate here in just a second. It's on the low side of the transformer. Okay, so you're going to use this and that nameplate data to come up with some values that I'm going to ask you to calculate. I'll send you an email on that. You're going to do a little engineering. Didn't even know you were going to do it, did you? Okay, so here's the low side of the transformer. And typically you've got the nameplate will usually be somewhere in this corner. You got all the instruments and the fill valve over here, the pop-off valve. If anybody knows anything about a hot water heater, you got a pressure release valve in there. Well, you got one on a transformer. It can get too hot. Also, down here at the bottom, there's a sample oil valve. And I can go in there and pull a sample of the oil, send it off to somebody, and they can tell me whatever is wrong with it. And then if you look in here, you'll see that you have an XO value, an X1, an X2, and an X3. We'll get a little bit more into that. That's the low side. High sides are always H, low sides always X. So here's the nameplate, and it tells you everything there is to know about this transformer. It tells you the kVA rating. It tells you the high side voltage. It tells you the low side voltage. It tells you how the high side is connected, delta. It tells you how the low side is connected, Y connected. It tells you how it's connected internally, right here, the actual internal connections and how you see them in there. Here is the tap changer values. Let me slide this over a little bit so you can see that a little better. There's the tap changing values. And so this is the rated values. Once again, this is our rated, rated. And this is three-phase power, because it's a three-phase transformer. It says so right here, three-phase transformer. GE ProLab tells you how much it weighs, how much oil is in there, all that good stuff. Tells you the serial number, just in case you have to parallel a set of these transformers. You can send GE that serial number. They'll find out exactly what the impedance of the transformer is, and they'll match it to this one, to your new one. Match this one to your new one. Don't have any problems. And these are your windings. So you see these little things right here. That's your winding. High side and low side. Okay. Tells you everything you want to know about this transformer. That is the most important thing in this transformer. By the way, I'm just going to let you know that we don't test our transformers. We run our transformers to failure. End of story. It's easier to let the transformer fail than it is to pay. I think I tested about about 100 transformers, maybe a little less than 100. Probably about 75 transformers. It cost me $57,000, and that was in 2010. I never tested another transformer. So you got the fill plug, you got the pressure gauges. You actually have two in this one. You also have the pressure relief blow-off valve right here. You have the temperature gauge. Again, down at the bottom, you have the oil valve that you can test the oil with. And then here's your cable. The color code on the low side over here is, in this case, X1 matches with H1, X2 matches with H2, X3 matches with H3, and as you saw, there were only 3 phases over there. Over here on the low side, you actually have a neutral, which is the gray phase right here. The gray phase is the neutral. Once again, you have a Y connected with a neutral, and they're 180 degrees, 120 degrees out of phase. So if you go back, let's see if we can see this. Let me see if I had this down. Where are you? Yeah, there you go. Notice there's no XO or HO phase in here. If this was a Y-connected transformer, it would have an HO phase for a neutral. Typically, in most high sides, they don't use Y. They can. They usually just ground that XO. They don't put an actual neutral on it, for the most part, as a general statement. Some people do, some people don't. Okay. So we've covered the nameplate, the sample oil valve, how it's connected, the nameplate, the wire. Okay, last but not least, actually it's not last. Inside that vault, that concrete box, this vault is about 36 inches deep. Notice I have excess cable in here. Notice there's excess cable. It curls around and goes down in a conduit right over there somewhere. And also on the low side, I have extra cables over here. Oh, something I did forget. On this low side, notice all the parallel conductors. What do we have? We've got 3 parallel conductors, 3 sets of parallel conductors. There you go. A parallel connection. Why did they parallel that stuff? Well, probably they used copper wire, and the bigger the wire, the more expensive it is. So I can run the same amount of current in 3 wires as I can in 1 bigger wire. So it's cheaper typically to run 3 conduits and 3 smaller cables than it is to run 1 big conduit and 1 big cable per phase. So that you'll see parallel conductors, parallel phases of conductors in construction. If you decide to be into, if you like to go into consulting, parallel conductors, parallel sets of wires will be something that you will use quite often. And just to let you know, you always put an A phase, a B phase, and a C phase into a conduit along with a neutral and typically a ground wire. You never run all the A phases in 1 conduit, never, ever. And all the A phases or all the B phases in 1 conduit or all the C phases in 1 conduit. The reason is that, once again, don't forget, these things are 120 degrees out of phase. So if I ran all the A phases in 1 conduit, I would have a huge magnetic field, and it would generate heat, and it would burn those cables up. Where if I have an A phase, a B phase, and a C phase, and I add the A phase current and the B phase current and the C phase current together, I get 0 current. Thus, the magnetic field is eliminated. The total magnetic field is eliminated in that conduit if I run an ABC phase in the conduit. Instead of running all A phases in one conduit, all B phases in one conduit, and all C phases in one conduit. You never do it that way. You always run one A, one B, and one C. Now you can derate and run more than one or an ABC phase in a conduit. So you could run 2 or 3 sets of ABC phases in a conduit. But when you do that, you have to derate the wire, which also presents problems. So if you go back down here to the ground, well, I guess you can. I guess you can. Maybe you could barely see it though. They have an ABC phase in this conduit. They have an ABC phase in that conduit, and right behind here they have another ABC phase. And in each one of those they have 4 wires and a ground. Here's your ground wire right there. So they have 4 wires. They have an A, a B, a C phase, and a neutral and a ground wire in each one of those 3 conduits. And that way they spread the wealth. The magnetic fields cancel out and the currents cancel out. Now when I get inside, I got currents, but that's the way it is. Anybody ever wrap up an extension cord around a wire reel and then you plug one end into the wall and then you're really pulling a big load over there on the other end, and you know most of it's wrapped around this reel or wrapped in a coil, or they're in a coil. Well, if you're really using a big load and you use it for a long time, it will actually melt that insulation, because what you have there is a great big coil of wire that has a great big magnetic field going on around it, and it gets so hot that it melts the insulation and it'll melt it. I have actually done that when I worked in the field a long time ago. Not a pretty sight. Okay, so notice that there's coils of wire in the bottom of this thing. There's spare wire in there. So the question is why is there spare wire in there? Well, I can tell you why there's spare wire in there. Because if I have to go in and one of these elbows goes bad, or one of those terminals go bad, there you go. That's what happens when they go bad. They blow off. Notice there's the elbow. That elbow used to look like that elbow, which used to look like that elbow at the beginning of the presentation here. What happened? Well, we really don't know. This happened over in Alamogordo about 2 or 3 weeks ago. They lost power to their campus, and luckily, down in their vault, they had some spare cable, so they came up, they cut off about 2 feet of cable, and they started making another elbow with 2 more feet of cable. So typically, excuse me, it takes 4 to 6 feet of cable to repair an elbow. And it depends on how far it's burned back. Notice that this is the B phase. In this case, 1 wrap of tape is the A phase, 2 wraps of tape is the B phase, and 3 wraps of tape is the C phase. Supposedly. Anyway, that's what's going on. That's the video for today. I'll get this up on YouTube here in a little bit, and I'll send out a little lab I want you to do. You're going to do some engineering for me using that formula backup in there. Again, nominal is what you have, the voltage that you have, and the rated voltage is what is the transformer rating. Okay? All right.